Hello everyone. Today we will share some knowledge about secure boot on the M460 series. We will introduce it from the following 4 chapters. First, it is a generality for the secure boot. The second is the implementation of secure boot. The third is to introduce the steps for configuring secure boot for users. Finally, there is a practical demonstration of the secure boot function of M460. Firstly, introduce the secure boot function. Secure boot is one of the important safety features of the M460 series, used to ensure the integrity and authenticity of device firmware and prevent malicious code attacks. The current industry application scenarios are as follows. Anti-firmware tampering. Ensure the security of OTA updates in IoT. Secure boot chain for payment terminals or identity authentication devices. So how to implement secure boot on M460? The secure bootloader is a built-in bootloader in the M460 mask ROM. For secure applications in the M460 series MCU, secure boot verification is implemented in the secure bootloader to verify the signed image before executing the image. The integrity check mechanism is based on SHA-256. The authentication mechanism is based on the ECC P256 ECDSA, elliptic curve digital signature algorithm. The signed image format is MCU boot compatible signed image. How is the startup process of M460 series? As shown on this page, it is the initial boot up code. After power on or a cold boot, the system first enters the bootloader in the mask ROM region, which contains the secure boot program. It then jumps to the user application. So next, let's learn about the detailed boot process of bootloader. This diagram shows the process of bootloader startup. We can see that, at the beginning, a self-check will be performed first. Then, if passed the self-test, the ROTPK will be checked for a value to determine whether to enter secure boot process. Of course, besides the ROTPK value, it is also necessary to determine whether to enter secure boot by using ALock or KSP lock to determine if it is in a locked state, which will trigger the entry into secure boot. The above introduces the principle, so what should be the actual implementation method for our users? Here are some examples. At present, we have an AN0063 document that provides a detailed introduction to the implementation method of M460's secure boot. Users need to carefully read the AN0063 document to understand the secure boot function and process of M460 in order to better master it. The implementation of a secure boot process is shown in the diagram. The first step is for the bootloader to ensure firmware integrity through hash. The second step is to verify the firmware signature using the ECC 256 algorithm with the public key stored in ROTPK calculation. At last, after passing the above 2 steps, proceed to execute the firmware. The bootloader on the left cannot be modified, and ROTPK only has one write opportunity. The firmware with the signature on the right is burned in flash, and the data structure is shown in the sequence from image header to ESDSA 256. How do developers configure the secure boot function of M460? The following 4 configurations are required. 1. Create key pair. Use the ICP tool to generate ECC key pairs, with the private key used for signature and the public key burned into ROTPK. 2. Sign image. Sign the firmware with ICP tool. At first. 3. Program the key and image. Program the public key into ROTPK and then program the signed firmware to flash. 4. Execute secure boot. MCU start secure boot process through checking ROTPK. The specific diagram on this page is clearer. Developers need to implement secure boot, configure the ROTPK public key first, and then sign the firmware in the EEPROM area. Afterwards, after burning through ICP, the bootloader will determine the firmware integrity and signature verification based on ROTPK and EEPROM data and then enter the main program. Finally, we will introduce the practical demonstration used NuMaker M467HJ. The printed result is shown in the left figure through VCOM. The signed firmware has been correctly executed after secure boot. Next, let's watch the demonstration video. First, open the ICP tool and confirm that the connected chip is M467HJ. Then, we will open the example code BPWM capture. To open the project, you need to set the start address to 0x400. And then compile and generate a bin file. Copy the bin file to the secure file directory to be signed. Then open the ICP tool and select Create Key Pair and Signature. After opening it, first click the Generate button to generate the key pair. The .c file is used for programming the ROTPK. Next, we use to create a signed image. First, load the newly PEM file as the key, then load the bin and click on the sign to generate the signed image. Afterwards, we will load the signed bin document on the ICP interface APROM. Afterwards, the ROTPK selects the generated .c key pair file. Then click Start for programming. After the programming is completed, press the Reset button on the NuMaker board to see the printed information as shown in the diagram on the right. From the demonstration, it can be seen that the total 4 operation steps. The first step is to create the key pair through ICP. Generate a public key file for PEM and .c suffix files. Use the public key file for ROTPK burning. The second step signs the firmware to be signed by loading a PEM file. The third step is to use ICP tool to burn the C and bin files generated in the first and second steps. After burning, the OTP position will have the OTP key 0 and OTP key 1 marked as used. After the burning is completed, the fourth step is to reset or power on again. Check the printed information to confirm if the image has been executed. The above is an introduction to the secure boot function and implementation method of the Nuvoton M460 series for help to achieve the function of safe startup. Follow the instruction file AN0063 in the software configuration process. It can help us quickly master the development of the secure boot function for M460 series products. Thank you.